What is going on, guys? Welcome back to the channel. In this video, we'll be talking about limit laws. The whole goal of this video is to give more insight on the limit laws mentioned in the last video by giving more examples, using limit laws to solve limits, and then also talking about the theorems that are results of these limit laws. Let's hop right into it. In the last video, we talked about two functions, f and g, and also a constant c. And all these values were separated by two different operations, or by one or more operations, and we could also find a limit using these laws. So if the functions are f and g are separated by addition, subtraction, multiplication, division, we could easily just split them apart. If we have constant multiples, we could factor out the constants. If we have any powers, we could raise the whole limit to a power. We also have a direct substitution rule. I forgot a rule in the last one, and what this rule was the limit as x approaches a of the nth root of f of x. Instead of taking this limit here, we could take the nth root of the limit of the function instead, making it easier to find limits. So instead of taking the limit as x approaches 3 of the cube root of x cubed plus 2 over 9x plus 1, we could take the cube root of the limits as x approaches 3 of x cubed plus 2 over 9x plus 1. All right, let's do an example. And the example today would be a rational function. Rational functions, when it comes to limits, are a continuous function as long as we're in the domain of the function. And we'll prove later, or not really prove, but we'll state later that we could direct substitute later. And so the limit we're going to be solving today is the limit as x approaches minus 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. And the first thing I would do is I would split the limits up. In the numerator, we have x cubed plus 2x squared minus 1. In the denominator, we have the limit as x approaches minus 2 of 5x minus 3x. All right, then we're allowed to split up into parts even more because there's operations. So we have the limit as x approaches minus 2 of x cubed plus the limit as x approaches minus 2 of 2x squared minus the limit as x approaches minus 2 of minus 1. In the denominator, we have the limit as x approaches minus 2 of 5 and the limit as x approaches 3x x approaches minus 2 of 3x. All right, so because this is a power, we are allowed to directly substitute. So minus 2 cubed plus, all right, so there's a constant here, so we pull the constant outside the limits. So we have 2 times the limit as x squared, as x approaches minus 2 of x squared, and the limit of the constant is 1. So minus 1. So minus 1. All right, so it'll be just minus 1. All right, sorry, that should have been 1. I made a mistake there, writing it out. Okay. And in the denominator, we have a constant here, so the limit as x approaches minus 5, or x approaches minus 2 of 5 is 5. And we have a constant, here, we could pull it out, giving us 3 times the limit as x approaches minus 2 of x. So directly substitute here, we get minus 8, and here as well too. We have minus 8 plus 2 times minus 2 squared minus 1 over 5 times 3 times minus 2. And after we simplify this down and clean it up a bit, we get minus 1 over 11. Okay, so talk about the theorems I was mentioning earlier. So the first one, they're not in really any particular order. This results in the squeeze theorem. It results in the squeeze theorem later. All right, and that's a whole different can of worms. That's a very important tool when we can't find limits using algebra. And so what this theorem states is if f of x is less than or equal to g of x when x is near a and except possibly at a. So not necessarily at a, but anywhere before it. And the limits of f and if the limit of f of x and g of x exist, then the limits of each of the functions, the limit of f of x is less than or equal to the limit of g of x. And so graphically showing, all right, this is our g function, this is our f function. All right, if this function So our g function's greater. It's greater here. It's above the f function, so meaning it's a greater function. As we approach a, this value a, all right, the function g is greater than a or f when it approaches a. So the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Sorry about that, guys. All right, so our second results, in no particular order, I just numbered them differently. I have them out of order just because my notes are out of order. So pretty much, there's another theorem. All right, if we have a function, f of x and g of x, and they equal each other when x is not a, then the limit of f of x is equal to the limit of g of x if the limit exists, if both limits exist. What does that mean? All right, so graphically showing, it'll be 2 lines. The easiest way to show this would be 2 lines. So we have a filled in hole here in this line here at a, and at this point we have a hole. This is our f. This is our g. All right. So at a we have this point on f that's a hole, and on g there's a point with a hole in it, but there's a point above it. So the functional values aren't the same, but the limits will exist. But the limits are the same. So the limit as x approaches a of f of x, and this is going to be L too. So the limit is L, and the limit here is L. All right. So the limits are equal. And the last one I want to mention is, this is very important. All right, the biggest thing you guys can take from this video is the direct substitution property, or the direct sub rule. All right, if we have a function that is a rational function or a polynomial function, and our approaching value a is in the domain of a function, then we could directly substitute. So what this is saying is, if we have a rational function or a polynomial, and a is in the domain, so this has to be in the domain. All right, we can take the limit of it, and it'll be the functional value. So an example of this would be the limit as x approaches 3 of x squared. Okay, if we take that limit, because x squared is a polynomial and 3 is in the domain of polynomials, we could say this is 3 squared is equal to 9. Okay. All right, and this is due to functions being continuous in the domains of their functions. So in their domains, the approaching value is in the domain, and the function is continuous. We could directly substitute. If we couldn't, we would have to use these limit laws, of course. And so later on, we could prove later on if you guys would let me, if you guys want me to, or if you guys would like to see it. Let me know in the comments down below. Just let me know, and I'll gladly do it. And so we could directly substitute with any of these: polynomial, rational, exponential, radical, logarithmic, trigonomic, inverse trig functions, as long as we're in domain. As long as we're in the domain, we could directly substitute. So this is where your pre-calculus comes in quite a bit, because you guys need to know the domains of these basic functions to be able to find the domain, to find the limits. Not the domain, but the limits. Okay. With that being said, guys, in the next video, in the next coming videos, we'll talk about the squeeze theorem, and then we'll also talk about these videos doing these functions, the limits of these functions using algebra. See you guys next time.